All right, thanks, Trish, and welcome everybody. Give me a second here. Looks like I've got a delay on my computer. There we go. As the title of the presentation indicates, I would like to talk a little bit about code-compliant construction for conventionally framed roofs and roof trusses. First thing I'd like to do is give you a definition. This is from the IBC, International Building Code, but conventional light frame construction is defined as a type of construction whose primary structural elements are formed by a system of repetitive wood framing members. And then they invite you to see section 2308 for conventional light frame construction provisions. Basically, since this is based on a prescriptive approach, conventional construction is necessarily limited in its applicability. And that we're going to be talking about the IRC today primarily, but there are also prescriptive provisions in the IBC as well. Now it's important to understand what the related requirements are. At times the code can be confusing or seem to omit relevant information. And obviously a poor understanding of the requirements can result in be costly both in terms of time and money. The structures and structural or construction systems that fall within the scope of the prescriptive code requirements would be detached 1 and 2 family dwellings and townhouses with separate means of egress. And then, as we just previously indicated, light frame construction, both platform and balloon frame construction. And I believe the vast majority of light frame construction that's built today is would fall into the platform construction requirements or definition. A little bit of background. The code allows, and when I'm talking about the code now, I'm really referring to the IRC. And this presentation, some of the references are actually based on the 2015 version of the IRC that may or may not be adopted in your locale yet, or it may not be and end up being adopted depending on what type of a code acceptance cycle the various locations are based on. But anyway, this is basically taken from the 2015 IRC. Anyway, the code allows portions of a structure to be engineered in accordance with the International Building Code without requiring that the entire structure be engineered. That's in section R802.1.1 so that this basically means then that some portions of the building may be engineered, i.e. the trusses and other components, but the structure may still be able to utilize the IRC prescriptive requirements. So let's kind of put a box around what we're talking about in terms of, we talk about the prescriptive code compliance. First of all, there are limits in terms of what loads can be applied to the various members. Roof live load. Now we're not talking about snow load here. We're talking about actually like a construction load. Maximum allowed is 20 pounds per square foot. Ceiling and floor live loads, there's provisions in there for 10, 20, 30, or 40 pounds per square foot. Snow load up to 70 pounds per square foot. 2015 IRC now incorporates the ultimate wind design. So the wind loading provisions have gone up to a ultimate wind speed of 130 miles per hour or 140, depending upon where you are in the country. The 2012 and the 2006 were based on the allowable wind speed, and so that's why there's a difference. It's not that they've jacked the wind speeds up. It all depends. It's all based on how the wind pressures are calculated now. And then the seismic provisions really haven't changed. For townhomes, it's seismic design coefficients C, D0, D1, and D2. And for 1 and 2 family, it's maximum allowed is D01, D02, excuse me, D01, D0, D1, and D2, and the exempt would be anything that is located in an A, B, and C. As far as structure geometry, typically what we're talking about for story height is 11 foot 7 inches, although you will see some tables in the code that reference a 12-foot story. I think that's just rounded up. Basically with a maximum laterally unsupported bearing wall stud height of 10 feet. And then in addition to the 10 feet, you're allowed to go with a up to 16 inches for the floor framing. Now I've got that couple asterisks on that because there are in very limited applications, there are prescriptive provisions that allow you to go up to bearing walls up to 20 feet. And again, this is using sawn lumber. The maximum number of stories would be 3 stories above the grade plane. Building width perpendicular to the ridge typically is limited to 36 feet. Building length parallel to the ridge, depending upon what type of product you're looking at, sometimes it's clear, sometimes it isn't, but basically it's 60 feet. Like I said, if you look in R802.1.1 applicability for cold form steel, they're very specific. Wood, you really have to look. It doesn't really say much, except if you look in the applicability limits that are listed for the wood trusses in R802.10.2.1, there it talks about 60 feet, and then in the commentary it throws wood trusses in with rafters. So that's where I'm coming up with the 60 feet there. And then mean roof height, depending again what we're looking at, it varies by what table you're looking at in the building code. The basis is 30 feet if we're talking about braced walls, so lateral load applied to the building. But mean roof height, if we're talking about uplift, then they use a basis of 33 feet. And both then you can, there are allowable adjustments that allow you to go a little bit taller than that as well. And then finally, some floor and roof geometry. Building width perpendicular to the ridge, okay, the previous slide showed 36 feet, but that basically is 36 feet plus a maximum of 24-inch overhang on each side. So you come up with 40 feet, and where you can back that number off is when you go to the header tables in Chapter 6, header and beam tables. That's where you determine what they're based on, and it's a 40-foot tributary, or excuse me, 20-foot tributary. Floor joist spans, the span tables go up to 26 feet, or just up to, just prior to 26 feet. Good luck finding sawn lumber that's gonna 26-foot 2x12. Same thing with the rafter spans. They, again, will list up to 26 feet, and ceiling joist spans also up to 26 feet. The maximum on center spacing that's assumed is up to 24 inches on center, and the roof pitches are between, well, excuse me, including a 312 up to 1212, or actually, or greater. Any roof pitch with a slope that's less than 312, the rafters or roof joists now need to be supported by structural beams, not a ridge board. So that's one of the limitations that they put on it. So anyway, when you look at the what the applicability limitations are of the IRC, a structure like this probably would not fall under that. There are alternate provisions that are allowed in R802.1.1. The following standards are permitted, subject to the limitations of the IRC and the limitations in the standards. And then again, as we mentioned earlier, when you get into situations, certainly engineered design can certainly be done, and that needs to be done in compliance with the International Building Code. But from a wood design perspective, item number 1 is the, and it's actually, well, I took it right out of the code. It's actually the American Wood Council now, their wood frame construction manual, which is a very good document, provides a lot of good information. There's also the AISI standard for cold form steel framing, also another very good document for 1 and 2 family dwellings. And then the ICC standard for design and construction of log structures. Those are alternate provisions that can be used. Finally, and perhaps the most important in terms of prescriptive code compliance, is that the construction documents per R802.1.1 should be of sufficient clarity to indicate the location, nature, and extent of the work proposed, and show in detail that it will conform to the provisions of the code. Now, this is right out of the code. Those of you that are on the call that work for component manufacturers in the design group, I'm sure all the construction documents, house plans that you see meet that requirement, easily meet that requirement. The other is that the construction of buildings and structures in accordance with the provisions of this code shall result in a system that provides a complete load path that meets the requirements for transferring loads from their point of origin through load resisting elements to the foundation. Now, obviously, when you load up in an actual structure, the load's going to work its way down from the top to the bottom, and it's ultimately going to get there one way or the other. Ideally, you'd like to have the correct framing members in place so that as the load accumulates going through the structure, the members that are helping to transfer that load down into the foundation, into the ground, through the foundation, into the ground, are sized correctly, both from a strength standpoint and a serviceability standpoint. Obviously, when someone is building, they're building the structure from the ground up, but the structure is being designed and the loads are accumulating really from the top down. So from a load path standpoint, we have loads in the vertical direction, which are typically gravity loads or loads that are influenced by gravity. And then you also have wind uplift loads. And then from a lateral standpoint, both acting parallel and perpendicular to the structural element, you can have lateral loads that typically the type that we're most familiar with would be loads from wind pressure and then from seismic activity. So the main thing then is with conventional framing, to be in compliance with the code, you've got to basically have a good load path through the structure. And sometimes this can be very complex in terms of how it's done, or how it actually occurs. So we're going to be talking basically about roof and ceiling construction today. And if you look in Chapter 8 of the IRC, and for those of you that are not overly familiar with the IRC, basically it breaks down the different areas that it's looking at in a chapter, by chapter. So for instance, Chapter 5 has to do with floors. Chapter 6 is wall construction, and then Chapter 8 is roof and ceiling construction. Things are handled a bit differently in the IBC, where they basically have a chapter that is specific to wood construction. That's Chapter 23, and so they're the various applications for that wood, whether it be in a wall, a floor, a roof. They're all included basically in that chapter, or referencing other chapters. But in Chapter 8 of the IRC, that's roof ceiling construction. And basically the prescriptive requirements for conventionally framed roofs, which can include roof trusses, are provided in Section 8.2 of the International Residential Code. And again, looking at the code, and we'll go into a little bit more depth in certain sections here, but basically what we're looking at in this case of a conventionally framed, stick-framed roof, we're looking at the ridge connection, rafters, collar ties, the ceiling tie, purlins, which basically are providing support for the rafters, and then purlin bracings, purlin braces, which are transferring that load down into interior load-bearing partitions, among other things. So if we look at Chapter 8, basically it's divided into these 11 sections. 802.1 is some general requirements. This typically gets into if you're using lumber, okay, that it's got to have a grade stamp on it, and that it has to be from an approved source, and it talks about the standards and so on and so forth. R802.2 talks about the design and construction requirements. Point 3, framing details. Point 4, allowable ceiling joist spans. Point 5, allowable rafter spans. Point 6, bearing considerations. Point 7, cutting, drilling, and notching, which certainly all framers and people in the trades, from what I've seen in doing truss repairs, everybody's familiar with those requirements. Lateral support, framing of openings, wood trusses is in R802.10, and finally R802.11 is roof tie downs. I might also backtrack here a second. I don't want to, we're obviously talking mostly about wood construction today, but on this particular slide, R804 in Chapter 8, it basically provides a prescriptive requirements for cold form steel roof framing. And obviously, being the Structural Building Components Association, I don't want to ignore that or those members that are involved in that. R804 is a fairly new section that was added. It's probably been in the code now, probably going on about 20 years, 16 years. It's very well done. They had the benefit, I think, of basically looking at how the building code, what was included leading up to it, and then have done a really nice job of laying out what the prescriptive requirements for framing with cold form steel. Like I said, it's they've done a really nice job of laying out what those prescriptive requirements are. Okay, so moving along, obviously, if you're working with lumber, the code requires that any load-bearing dimension lumber that's used for rafters, trusses, ceiling joists, studs, what have you, floor joists, shall be identified by a grade mark of a lumber grading or inspection agency that's been approved by an accreditation body that complies with the Department of Commerce Product Standard 20. And we won't get into what all that is, but basically you need to have a grade stamp, and that grade stamp, in this case, TP is the Timber Products. They are an accredited inspection agency. And this particular piece is Southern Pine. The mill number was 658, and its grade is a number 2. So that is a visually graded piece of Southern Pine lumber. The KD means that it was kiln dried to a moisture content of 19% or less, and then during that process, the temperatures were high enough to basically be able to put the HT, which means heat treated. That really comes into play in terms of shipping this lumber and having to worry about insects, larvae maybe being in the wood when the lumber was cut, and then that larvae stays alive during the manufacturing of that lumber, and ultimately remains alive after that lumber is installed in the structure. So in this case, it was heat treated, so the temperature was high enough that it should kill any type of insects that might have been in that lumber. R802.1.1.1 talks about end jointed lumber or finger jointed lumber, and basically finger jointed lumber is allowed. Structural finger jointed lumber that's stamped with a certified exterior joints may be used in rafters and trusses. The picture on the right is of a, as you can read, says vertical use only. And in that case, what that means is this lumber should never be used when it has that stamp on it, vertical use only, should not be used in structural applications with long-term sustained bending or tension loading, sorry, not of, or tension loading. So if you're ever out on a job site and you see vertical use only being used horizontally, that's not a good thing. Basically, the type of adhesives that are used in a product like this are such that they can be used as a stud in a wall, but not in terms of in anything that a rafter, joist, or in a truss member. So Section R802.2, Design and Construction, basically says that the framing details in R802 apply to roofs having a minimum slope of at least 3 units vertical and 12 units horizontal or greater. Roof ceiling shall be designed and construction in accordance with the provisions of this chapter and figures R606. A couple of figures in R606 that basically is the prescriptive, some of the prescriptive, those figures deal with some of the prescriptive requirements for concrete masonry unit construction in terms of how to tie or how to support the wood on the wall, on a CMU wall, and how to provide uplift connections and things like that. Or you can use the American Wood Council's National Design Specification, NDS. And then components for roof ceiling shall be fastened in accordance with table R602.3. So that's in R602.3 is in the wall chapter. And that is a rather lengthy table that basically provides prescriptive connection requirements for a whole bunch of different types of connections. And we'll talk about that here in a minute, or get into a little bit more specifics on that a little bit later in this talk. R802.3, framing details, provides some basic framing details for ceiling joists and rafter connections, ceiling joists that are lapped, and then blocking. So what are we talking about here? Okay, in a rafter connection, rafters basically tying into a ridge board for slopes where the roof is greater than a 312 pitch. You're allowed to use a ridge board, and that ridge board basically functions, it's non-structural. What you're doing with true rafter framing is you're kind of building, field building a truss. So that rafter is not there to help, support a tributary load that's applied, gravity load that's applied to the rafters. It's basically there to provide a something that the rafters can push against. And the code allows that the rafter framing can be offset up to 1.5 inches on either side of the ridge board. And if you're for valley and hip rafters, there you need to use a minimum 2-inch nominal thickness, whereas a ridge board, you're allowed to use a 1-inch nominal thick piece. And whether it's a ridge board or a valley or hip rafter, the ridge board or valley or hip rafter has to be at least as deep as the vertical dimension after it's been cut of the rafter that's tying into it. So that's what the figure in the upper right-hand corner shows, that the depth of the ridge board or valley or hip rafter, A, that dimension has to be deeper than B, which is the vertical dimension of the rafter tying into it. And then again, to reiterate, if you have a roof slope that is less than a 312, then everything, the ridge and hips and valleys have to be designed as beams. So these are some framing details that basically, courtesy of the commentary to the IRC, again, indicating that if in a true ridge, the figure on the left, in a true ridge board application, minimum 1 inch nominal is allowed. Not sure of anybody that's actually using a 1 inch or a board anymore, but it is allowed. And that the minimum depth of that rafter, the ridge board, has to be at least equal to or greater than the vertical depth of the rafters tying into it. Now, if you don't want to use a ridge board, you are allowed to use just butt the 2 rafters up together and then apply a gusset plate nailed to the side. That is acceptable. Unfortunately, the code really doesn't provide much guidance in terms of what that gusset plate needs to be, or the nails that, the type of nail that needs to be used to attach that the gusset to the rafters. There's also provisions in R802.3 that discuss the requirements for collar ties or ridge straps. And first and foremost, the ridge straps that go across the top in this case, or the rafter ties, or collar ties, I should say, they're basically there to resist wind uplift. The collar tie would need to be located in the upper 1/3 of the attic space. The collar tie can be or as small as a 1x4 or greater, and then the spacing is less than or equal to 4 foot on center. Now, again, 1x4, there was a time when 1x4 boards were fairly common. Today, unfortunately, you'd be really hard pressed to find a 1x4 that is actually graded for structure. The vast majority of 1x4s that are produced today are graded under architectural rules. The wood is still there. Unfortunately, it's very difficult when it's the way it's graded. You can't put a design properties on that material. Those of you that have been in the truss industry long enough know that about 20 years ago, it wasn't that uncommon to see 1x4s specified for lateral restraint or even web reinforcement. The problem with trying to use a 1x4 today, again, is they're not graded for structural applications. They're graded for architectural, and so it's very difficult unless it's regraded to put design properties on that product. Some of the connection requirements for attaching the roof rafters to the ridge or valley or hip are provided in that table R802. And again, this is some excerpts from there. In this case, that lower box that you see in the upper right-hand corner says a collar tie to rafter requires face nails or 1/4 inch by 20 gauge ridge strap to rafter, and then calls out what the minimum number of nails that are required. And the upper two, the 410 penny and the 310D common, those are typically hand-driven nails. So the only nail that's included in this little box here that would be in your typical gun nail would be the 3 inch by 0.131. And again, that's a face nail application that's going to be used. R802.3.1 also provides information regarding rafter ties. They are required where ceiling joists are not parallel to the rafters, where ceiling joists are not continuous or securely joined, where ceiling joists are not connected to the rafters at the top plate. They would need to be at least 2x4, and you find information regarding the rafter spans and the requirements are in tables R802.5.1, tables 1 through 8. And some additional information that's also included in R802.3, again, get into some specifics in terms of toenailing the ceiling joist and the rafter to the top plate, and then also the connection of that ceiling joist, in this case, to the rafter, provides information about when the ceiling joists are lapped to provide resistance to the rafter thrust. You have to have a minimum 3-inch lap and a minimum connection detail for that. Or if you want to butt the ceiling joists together, then they need to use a wood or metal tie strap. And again, and I've got a better diagram coming up here. What you're basically doing in the figure on the right-hand side, in this case, the ceiling joists are parallel to the rafters. What you've basically done here is you've designed a, let me see, I'll get my pointer. Oop, hold on a second, sorry about that. Anyway, in the figure on the right-hand side, you're basically, they're field building a truss, okay? In this case, it has no webs in it, but you've got the rafters that are forming kind of like the top chord. They're in compression and resisting the gravity loads and bending. So what's gonna happen is that ridge board is not structural, so the rafters are pushing against it, and that's gonna create a thrust at the bottom, which ideally is going to be taken out through the ceiling joists, which are basically right at where that rafter meets the bearing elevation. Okay, the figure on the left-hand side, in this case, the ceiling joists are not parallel, so you have to put in the rafter ties to resist that thrust. And so that's in addition to the ceiling joists. And in the figure on the left-hand side, the ceiling joists are not resisting or any thrust because obviously they're running perpendicular to the rafters. So what are some of the connection requirements? And again, we're not going to get into the gory details of looking at the tables, but basically, the ceiling joist to top plate, again, there are prescriptive requirements for attaching the ceiling joist to the top plate. There's also ceiling joists that, when they're not attached to a parallel rafter, lapping over partitions, okay, what the requirements are. And then more importantly, when ceiling joists are attached to parallel rafters, in other words, in this case, they are resisting not only the weight of the ceiling, not only the weight of any gravity loads that live load that maybe have applied to them in the attic, but they're also helping to take that thrust or resist the thrust created by the rafters. Then you've got to go to table R802.5.1 9, and that, as you can see just from the little bit of table that we've got here in the lower right-hand corner of this slide, for a rafter slope of 312, rafter spacing at 24 inches on center, if my ground snow load is 30 pounds per square foot and my roof span is 36 feet, I need to have 21 nails, and these are 16D common per each heel joint splice to resist that thrust. The lower the slope, the greater the thrust. That's why it's, again, it's limited to 312 or greater. And again, just from the little bit that you see there, if it's 30 pounds per square foot ground snow load, if my roof span is 36 feet, if it's a 312, I need at 12 inches on center, my rafters at 12 inches on center, I need 11 nails. If it's a 412, I only need 8 nails, or not only, but it's less, because again, it's steeper pitch, so that the thrust is going to be less out at the outside wall. And again, these are all prescriptive requirements for rafter framing. Section R802.4 talks about ceiling joist requirements. Again, you size what you need in terms of the species, the on-center spacing, and the size. That's provided in tables R802.4, 1 and 2. Maximum spacing or spacing is between 12 inches. They provide 12, 16, 19, 2, and 24 on center. The The size is between, well, 2x4 up to a 2x10. Maximum span that's listed is 26 feet. Actually, there are some instances where you're, you know, if the grade's high enough and the ceiling joist is of a great enough depth, like a 2x12, and the load is light enough, you can go greater than 26 feet, but you're not going to find lumber, sawn lumber, greater than 26 feet. In fact, these tables typically will just indicate that the allowable span is greater than 26, so you're limited to 26. And then they also have a footnote on the table that says contact the lumber supplier for spans greater than 20 feet, because that's really what you're kind of limited by in terms of what the availability of the material is. The ceiling joist tables in the building code are based on 4 species: Doug fir larch, hem fir, southern pine, and spruce pine fir. 4 grades: select structural, number 1, number 2, and number 3. Dead loads of 5 pounds per square foot and 10 pounds per square foot, and ceiling live loads of 10 pounds per square foot and 20 pounds per square foot. Jumping ahead a little bit, but in R802.3, it talks about, again, if that ceiling joist is used to help remove the thrust from the rafter, then it has to be either continuous or joined over any interior partitions, and that requires being lapped either at least 3 inches or butted over the bearing partition or beam, and then attached together with some type of a plate, metal or wood. The again, discussing some of the connections, which we've already kind of talked about. Obviously, that in this case, that's bottom cord, or excuse me, the ceiling joist is being used to take the thrust out, and so whatever the nailing requirement was at the where that ceiling joist ties into the rafter, if you butt that or connect 2 ceiling joists at an interior bearing, they also have to be connected in similar fashion. Rafters are discussed in R802.5, and again, some of the requirements for these tables: 12 to 24 inches on center, 2x4 to 2x12, 26-foot maximum span. That span is measured on the horizontal. So the one thing I want to point out here is, based on our sketch up above, that span would be 26 feet, in this case on the right-hand side, from the ridge board to the outside wall, measured on the horizontal. Or on the left-hand side, because you've got that Purlin brace in there, now that 26 feet basically would go from the ridge board to the location of that Purlin and Purlin brace, and then also 26 feet from the Purlin brace out to the outside wall. Again, measured on the horizontal. Species that are listed are the same as with the ceiling joists. The grades are the same. In this case, they've got tables for dead loads of 10 pounds per square foot to 20 pounds per square foot, and then roof live loads, including snow loads, of 20 pounds per square foot up to 70 pounds per square foot. If you're in an area that's got some other type of species than what's included in the building code, you are allowed to go to the American Wood Council's rafter. They've got a rafter booklet that basically includes other species that you're allowed to use. And the exact name escapes me, but I'll think of it. So structural member sizing. When we're looking at this, you know, this is an application in this case where it's a fairly steep slope. These rafters are quite long, and having to be quite long. And got a couple of problems here. They've got collar ties installed up near the top. I don't quite know what that beam or joist is that's going across kind of in the middle. Probably the thought there was it's helping to stiffen the roof deck. And again, this is a fairly deep pitch. But what's missing here, and probably is these were not designed, you're missing some type of, you'd have to have either a rafter tie or a ceiling joist, which I don't believe is going to be installed in this particular application. Now, the only way really to get around this would be to design the ridge board as a beam, which helps then, now that beam is going to help carry half of the load on that and transfer the other half of that vertical load, gravity load, is going to get transferred down to the walls. And by putting a beam in, you've taken a lot of the thrust out, in fact, pretty much all of it out of the rafter. But in this case, they haven't done that. You can't see the ridge board, but there's a ridge board there. But again, what's really missing from this is there's no either ceiling joist or rafter tie. And there are limitations in the span tables in the building code that say, okay, because the assumption is to get the full span that's listed in those tables, that ceiling tie needs to be down right at the bottom or at the ceiling level, where the rafter sits on top of the bearing. If when that ceiling joist or rafter tie, is raised, the higher you go, this factor that you see in this red shaded in area on the right shows what the reduction is in terms of the allowable rafter span, because what you're doing is you are introducing a fairly large bending moment and increasing the deflection, the flexure of that rafter. So again, the spans that are included in the rafter tables are limited in terms of how far you're allowed to span and where that rafter tie is located. The assumption is it's right at the bottom. The connection requirements, again, this is for uplift. The prescriptive requirements in table R802.3 table 1 are for uplifts less than or equal to 200 pounds, based on a basic wind speed of 115 miles an hour, exposure category B, roof pitch 512, greater than or equal to 512, roof span less than or equal to 32 feet, and rafter spacing less than 24 inches, less than or equal to 24 inches on center. Okay, if you meet those requirements, then you're allowed to use the connections shown in the boxed area in the lower right-hand side of this slide. If you don't, then you've got to go to section R802.11 for tables that basically provide much higher, they don't call out what the connection is, but they do show what for various pitches and on-center spacings, what the uplift reaction is that you have to then come up with, or the contractor or the framer would have to come up with some type of a mechanical connection for. So not unlike trusses, basically, where it gives you a uplift reaction, and then based on that uplift reaction, they can then go and decide, okay, what type of a framing anchor I need to apply to the rafter. So again, similar to trusses, but a little bit different way of getting there. Purlins and Purlin braces, again, what we're talking about now is we're providing support to the rafter, which then allows us to increase the size of the building, if you will, by limiting the span of the rafter. And these Purlin requirements, they have to be, the size is greater than or equal to the required size of the rafter that they support. It has to be continuous and supported by braces. And the Purlin braces must be a minimum of 2x4 installed to the bearing wall at greater than or equal to 45 degrees from horizontal, unbraced length less than or equal to 8 feet, and spaced less than or equal to 4 foot on center. So again, what we're kind of looking at is here we got our rafter, we've got this Purlin brace that comes up, it gets nailed to the side of the rafter. The Purlin gets installed perpendicular to the rafters. It's installed tight up against the bottom edge of the rafter, and it is nailed off to the Purlin brace. There's also requirements in the building code for sawn lumber, and that limits what the cutting and drilling and notching has to be. In this case, if you're going to notch a rafter, the figure on the left indicates that the notch can be not less than, or that the amount of wood left above the notch can be not less than 3.5 inches, and the cantilever that extends past that notch cannot be greater than 24 inches. And then the maximum depth of the notch is the depth of the joist divided by 4. And then the figure on the right obviously is a taper cut that would be the size of the taper cut that's allowed either for a floor joist or for a ceiling joist. There are also requirements in Chapter 5 for floor joists, which would also apply for rafters that have allowable notch sizes, allowable hole sizes, and their locations. So again, I got to believe this is an area that not many people are aware of, because you see all sorts of holes and notches cut in joists as well as in truss members. Section R802.10 talks about wood truss requirements. The 10.1 has information regarding what needs to be on the truss design drawings. We think of wood trusses in this case as metal plate connected wood trusses, but they don't necessarily have to be. But in this case, if it is a metal plate connected wood truss, 10.2 talks about that it's got to be designed to ANSI TPI 1. And that's why you'll see that on your truss design drawings. So in terms of what's used, it's TPI 1. And then there are bracing requirements, and that can typically be, in this case, the IRC specifically references SBCA building component and safety for guide to good practice for handling, installing, and bracing of metal plate connected wood trusses. And hopefully everybody on this call is familiar with this document. If not, it's not a bad one to have in-house, a couple of copies. In this case, this document provides some of the industry recommended standard details for restraining and bracing trusses, whether it's the top cord, the bottom cord, or the webs. So when you put it all together, with all the requirements in Chapter 8, it can be fairly complicated. And one of the reasons for a presentation like this is, some of you are maybe in locations where it's not uncommon to have roofs stick framed, okay? And unfortunately, a lot of times, we hear the term stick frame and it's pretty much, oh, well, should be simple to do. It's really not that simple to do. It's very complicated. There are certainly requirements, and there's a lot of good information out there in terms of how to do it and how to do it correctly. Unfortunately, what you're going to see is in many situations, and you can have the same thing with installation of trusses, stuff's not done right. The guys that are actually doing the installing and everything really are not familiar with what's in the building code or what's in these various alternative provisions. And they're pretty much out there just doing what they feel works. And conventional light frame construction is very forgiving. Now, there's many areas that in the code that that really aren't discussed very well. There's not a lot of good information that's provided. There's no guidance. Some of these are bracing design for high end of a hip or valley rafters, bracing design for rafter purlins. Yeah, it talks about maximum unbraced length is 8 feet, but what are you supposed to do if you've got a tall roof and you've put the purlin in the purlin brace and it exceeds 8 feet? Then what do you do? Non-symmetric hip roofs, roof diaphragms with plate height changes, large roof openings that exceed 6 foot on center. These are basically all are not covered. There's no guidance in terms of the prescriptive requirements. Other areas that need to be watched closely and really can cause the most problems would be adequate load path, connections. Again, many of the connections that are called out are nailed connections. Okay, it does specify what type of nail, but how does an inspector know that what nail was used? So on and so forth. Supports of the rafters and the various framing members, and then structural sizing can also become a problem. Again, load path, that load is accumulating from a gravity load standpoint. That load is accumulating as you work from the roof down through the structure. And so typically, as that load accumulates and moves through the structure, you got the highest magnitudes occurring down at the first level of the house, and that all needs to be taken into account with sizing of the members. Now, in truss construction, loads are typically carried by outside walls and transferred down to the foundation wall. With conventional framing, construction loads must be transferred through the interior of the structure, because typically you're not going to be able to have rafters that are long enough to span from outside of wall to outside of wall. This can lead, obviously, to large concentrated load transfers through the interior walls, and sometimes these loads are terminated at a floor level, and they magically disappear, where in reality that load then has to get transferred down through the floor into some type of vertical load resisting element down into the foundation, and then ultimately into the ground. This particular slide just shows an example of how these loads can accumulate. And in this case, the roof live load or snow load that was used was only 20 pounds per square foot, and the dead load was 10. But you can see you get some fairly large magnitude loads that are being concentrated loads that are being transferred down through some of the interior locations. And there's a good chance that, you know, the beams that are, if there's a beam on the floor or floors as you work your way down, they need to be able to pick up those loads and transfer those loads to the load bearing walls and ultimately get them down into the foundation. Basically with, you know, like I said, load path can create a problem. In this case, the figures on the left, you've got a 3-ply LVL beam that is supported on some columns, which in turn come down and are supported on some plates on the floor. And the floor framing members, and this is during construction, so there's really not a lot of load on this roof, but the floor framing members were not sized to carry any concentrated loads. And as a result, you're already getting a dip in the floor. And you see the same thing with the figure on the right-hand side. Again, there's a dip in the floor because of some fairly substantial loads that are coming down and just basically sitting on the floor. And you can have the same problems, obviously, with trusses if loads are missed or the flow of loads are missed. This particular slide basically, or figure, or photo, shows a dormer framing that the dormer roof is being supported by a dormer wall, which once you get past that little cripple wall is basically the header that's coming across supporting the upper roof that ties in to the dormer. That header is being supported just on a single 2-ply rafter, which obviously is not a good thing. With trusses, obviously, in this case, you could design a tail-bearing girder truss, but you know, if you are able to follow the flow of loads correctly, it's going to require more than just a single ply. Again, with load path, whether using conventional framing or trusses, it's essential to pay close attention to the load path, especially with today's larger, more complex homes. And those loads accumulate as you work your way down from the top of the structure to the bottom. Common examples, and these could be trusses as well, where basically you know, they've got a multi-ply member, and if they're going to install any type of columns. They haven't done it yet on these two pictures. Interestingly enough, in the building code in chapter 6, the requirements, the plate material has to be greater than or equal to 2-inch nominal. The width is either greater than or equal than the stud width. Single top plates are allowed if the framing stacks on top of the studs. Well, it can be, you're allowed within plus or minus 1 inch. Double top plates, the rafters or joists can be within 5 inches of the stud beneath, unless the top plates are 2x6 or 2 2x6 or 2 3x4. And then if you use a triple top plate or blocking, the rafter or joist location is not restricted. But now we're talking about rafters or joists or trusses, not girder trusses, not girders, not beams. Those you're required to get some type of a column in that wall. And if you don't do that, you can certainly end up with something like this, where you get some severe crushing that takes place that ends up showing up through the gypsum. Couple things here regarding studs. The building code in chapter R802.3.1, where it lists the stud size, height, and spacing. You're allowed to use utility grade studs that are not spaced more than 16 on center. They shall not support more than a roof or ceiling and shall not exceed 8 feet in height for exterior walls and load-bearing walls, or 10 feet for interior non-bearing walls. Okay. When it comes to tall walls, the restriction number 2 is where snow loads are less than or equal to 25 pounds per square foot, and ultimate design wind speed is less than or equal to 130 miles per hour. 2x6 studs supporting a roof load with not more than 6 feet of tributary shall be maximum height of 18 feet where spacing is 16 inches on center, or 20 feet where spacing is 12 inches on center. Again, the key there is you're limited with your wind speed, ultimate wind speed. You're limited with what the snow load can be on that roof, and you're also limited to only a tributary of 6 feet. Then you're allowed to use studs up to 20 feet in length at 12 inches if they're spaced at 12 inches on center. I stress that because when you look in this table that of R802.3, notice in the second column from the left, laterally unsupported stud height that you're allowed for a bearing wall is 10 feet. And then obviously if it's a non-bearing wall, you're allowed to go taller. But again, based on that exception, you are allowed to go with a taller wall, but it's very limited in terms of how much load that can support. And I know there's a lot of, certainly some homes that are out there with great rooms in which that the studs that are in those outside walls do not meet that exception to that we just read. One interesting note, load-bearing wall is identified in the IRC as a wall supporting any vertical load in addition to its own weight. And then a non-bearing wall is a wall that only supports its own weight. A couple other items that can come up with load path. In R802.3, design and construction, studs shall be continuous from support at the sole plate to the support at the top plate to resist loads perpendicular to the wall. The support shall be a foundation or floor, ceiling, or roof diaphragm, or shall be designed in accordance with accepted engineering practice. And then they have an exception for jack studs and trimmer studs and cripple studs at openings and walls. But what that provision basically is saying is that this sketch that you see at the right-hand side that basically shows a tall wall with a hinge in the wall, that is not accepted for reasons that you can see in that sketch. Yet you do see that type of application used quite a bit. And that's not a good design or construction practice. And you can also see it happen with roof trusses, or if you're using trusses. Now in this case, this was a church sanctuary that was being built. So the roof trusses are scissors trusses. So there's a slope obviously on the bottom chord. They ended up providing a structural gable truss, but a flat bottom at the end of this sanctuary to make it easy, obviously, for the framer to frame that wall. But what you have is a hinge point where that bottom chord ties into the top of the wall. And if you I went over to this wall, and you could actually, just by applying some lateral pressure, you certainly could shake that. It definitely moved. There are, and in BCSI B3, basically they're, provide a caution in terms of it's not recommended to do that. That if you're going to have a situation, basically the top of the wall needs to be at the same elevation as what your ceiling diaphragm is, unless some type of special bracing is called out. Girder and header design requirements are provided in tables R802.7. Again, the sizes vary from 2x4 up to 2x12, maximum span of 14 foot, 4 inches. And again, these are sawn lumber headers and girders. The species, again, that are included in are Doug fir, hem fir, southern pine, and SPF. And again, the loads are live loads up to 70 pounds per square foot, dead loads up to 20. Connections. I've got about 10 photos to go, so if you can bear with me, we'll be done here in a couple of minutes. Connections. IRC includes fastener requirements for conventional construction within the scope of the code. Problems may arise when there is end grain nailing or where multiple members are joined. For example, nailing details like the one on the right with a compression block, where you attach the block to the side of the beam, and then in terms you're attaching the rafter to that, may or may not be sufficient. Certainly this connection where I've got some type of a valley that's tying into another bearing location, fortunately they didn't do a very good job of cutting that member either, but now you're trying to support that off some nails that obviously there's gaps there. You're not getting the full nail penetration on some of those nails, and that's just not a very good situation. The other basic problem with inspecting nailed connections is knowing whether the nails meet the code fastener requirements. Again, this table R802.3.1 provides prescriptive requirements for various types of connections between various building elements. And they usually provide several different nailing options, which include typical hand-driven nails, common wire nails, box nails, so on and so forth. And they list the nail length, the nail length, as well as the nail diameter, because that all comes into play in terms of what the lateral resistance, the allowable nail values are, depend on the nail diameter, the length, penetration into the member, the species, and so on and so forth. The hip rafter connections, when it's stick framed, it looks like they've done a very nice job on the photo on the left of cutting the members to get a nice tight fit. But how you connect them, that can create some problems. Whereas typically with the truss applications, some type of an engineered hanger or connector is going to be used to help transfer that load from those members into the supporting member. Another example that you see, and this can again happen with trusses as well. In this case, I've got ceiling joists that are tying into an LVL beam. Those ceiling joists are fairly shallow. They don't need to be any deeper because of the loads that they're supporting and the spans. Okay, that beam, because of its span, is deeper. So you've got a top edge of a beam that basically is up in this attic space that is not braced continuously. Yes, you do have some, it looks like some Purlin braces coming in on the top cord on the left-hand side of that. They're helping to brace the top of that beam, but they're also applying roof load to the top of that beam. And chances are, if this beam was sized, the sizing software that was used, you want to make sure that it tells you what the maximum unbraced length of that beam is or can be for the loads applied to it, to make sure that it's not assuming that that top edge of that beam is laterally restrained along its entire length, because this one is not. And another area where you can see if these problems can occur would be load-bearing garage door headers. In this case, it's a fairly large LVL beam, fairly highly loaded, and even before the project finished, that little cripple wall that sits between the bearing location of the roof trusses and then comes down and sits on top of the beam, you really have a hinge point between the bottom plate of that wall and the top edge of that beam. And to fully load that beam, that knee wall or cripple wall may not be adequate enough to resist that beam from wanting to buckle. And that's what you're seeing here with that 1-inch lateral deflection. So again, providing proper restraint and bracing for the various planes, just like with trusses, is very critical. The design of roofs of almost any complexity or size can be accommodated fairly simply with trusses. Especially, it's really nice with the design software that we have today that shows the 3D modeling. You can really visualize how everything's supposed to come together. The truss placement diagram shows how these are laid out. There's no guesswork on the job site about the roof. It indicates where the trusses, identifies which trusses go where and where the assumed bearing locations are. Doesn't take the place of the framing of a structural framing plan, but it at least provides some additional guidance for those installing the trusses on the field. Apologize, this figure, lower right-hand corner, didn't come out very well. This is basically showing a stick-framed framing plan, and I use that with quotes around that. Basically didn't really show much. All it did was showing the planes of the roof. Didn't really show how that was supposed to be stick-framed and where the assumed bearing locations would be. Engineered roof truss framing simplifies the creation of a continuous load path that's fully compliant with R802.1 of the IRC. The bracing and related connections can be found on the truss design drawing and in BCSI, and which also supports the requirements of the code to make it compliant with continuous load path. Showing a couple of notes that are on the truss design drawing. The one on top indicates that this truss, the design assumes that the top cord is restrained and braced with structural wood sheathing directly applied, or purlins at 6 foot on center. Bottom cord in this case is rigid sealing, directly applied, or purlins at 7 foot 6 3/4 inches on center. And that you'd have to look at the truss design drawing, but in this case, 1 row of continuous lateral restraints required on web 4 to 6. And then lateral restraints also required at joint 10. The note right below that is from a different truss design drawing that says web bracing is required at each location shown, and then it correctly refers the installer to BCSI for proper required lateral restraint, and then diagonal bracing, web bracing. So options to ensure that there's code compliant framing is, number one, you can hire an engineer, eliminate any ad hoc framing solutions, and then another option obviously is to use structural building components. And the bottom line is this: using trusses and building components can make the IRC code compliance much easier and result in more structurally accurate and higher quality buildings.